California, right? There we go. Okay. So yeah, I'm going to talk a little bit about our efforts to improve the fidelity of our thermal radiation models, despite what Donovan said earlier, which is kind of specific to our risk assessment for this, the PDC scenario. In specific scenarios, the luminous efficiency might prove to be important. And really what's motivating this work, as Donovan kind of alluded to, is that, this is probably one of the most uncertain, uncertain parameters that we have in the tool, in our parameter set that goes into these semi-analytical models. This quote comes from Collins, that it's not presently well constrained. I would say that's an understatement. So this is actually the range of potential values for luminous efficiency that go into our probabilistic risk assessment. So you can see that this spans 3 orders of magnitude. And I would say as a physics person, I would find that level of uncertainty pretty undesirable. So that's kind of what motivates this work. We're going to try to leverage high fidelity numerical simulation to try to generate a simulation-based luminous efficiency. So I would like to say that this is the kind of simulation that I'm going to use to generate these results. This is what we think an actual asteroid airburst might look like if you could peer inside. But of course, this is the simulation world, so we deal with spherical asteroids conveniently. So this is our asteroid for the purposes of this work. And in order to start to try to compute the luminous efficiency from simulation, we need to capture some pretty key phenomenon for asteroid entry flows. These are kind of unique compared to other entry flows in a couple of significant ways. Just because of the high entry speed, you get incredibly high temperatures in the shock layer. So you need to capture the radiation of the shock layer out into the environment. You've got an extremely high radiative heat flux that goes to the surface, which in turn causes massive ablation due to vaporization as well as melting. And all of that vaporization flows into the wake and remains at a high temperature. And that's what we see in the case of a bolide as light. And as we'll see in a moment, that's what we experience as thermal radiation, or hopefully don't experience in the case of a planetary defense scenario. So to capture all of these effects at the highest fidelity that we have available to us, we're going to solve the full reacting Navier-Stokes equations around our spherical asteroid. For this particular case, we chose a carbonaceous chondrite composition for the meteoroid. Without going into detail, it turns out that within the chondrite composition, at least for now, we don't think that that's a too significant of a choice. So in order to model all that, we account for 39 total species. I've actually gone to the trouble of putting all of those in there just to convey the complexity of these calculations. And then really, in order to compute these flows, because the energy is so high, you need to couple the radiation transport to the flow physics, as well as the ablation. So in order to get a reasonable luminosity, you have to have the ablation products in the simulation. So you see all this iron, and you even see some sulfur in there, and magnesium. So all those species are accounted for in this calculation. So before I kind of get into the thermal modeling, I just wanted to highlight a couple of physical insights that we can glean from our simulations, which were interesting. So one of the things we kind of wanted to take a look at is, where does the radiation come from in our simulations? This is relevant for both bolides and asteroid scenarios. So you have some trade-offs going on in here. Near the shock, you of course have the highest temperatures in the flow, but you have a pretty small radiating volume. As you move downstream, you retain some of that high temperature and have a larger volume. And then as you go further downstream, the flow cools. And so we can see and kind of quantify the different radiating regions. Here you see each of those regions. You see the radiating spectra within each region. And you can see that this kind of near wake region actually contributes the majority, or I guess the plurality of the radiation that's experienced on the ground. And so one of the results of this particular insight is that there's a strong view angle dependence to the radiation that you would experience on the ground, or the light that you would observe in the ground in a more benign scenario. So if you can imagine, if the asteroid is coming directly at you, which would be an unsettling experience to be sure, you're really not seeing the wake through the object itself. You're just seeing the shock layer, which is incredibly hot, but relatively small compared to the full bolide trail. And so you can kind of see that here in this plot, that there's actually an optimal view angle. In this case, 0 degrees is that scenario I mentioned where it's coming directly at you. And you really just see kind of this, albeit very hot black body, but not a lot of intensity. And as you kind of move around and observe the bolide or the asteroid coming in from the side, you see a lot more of that near wake region. And so you can imagine that there's kind of an optimal viewing angle or non-optimal viewing angle, depending on your perspective. So that's all well and good. Donovan kind of alluded to that as much as we might like to, we can't run these models within a probabilistic framework. These calculations are very expensive. So we need to figure out a way to reduce the output from these calculations into something that can be input into these semi-analytical models that we've heard about in the previous couple of talks. So in order to do that, we ran a database of calculations within planetary defense relevant regimes. So velocities going from 6 to 20 kilometers a second. Diameters from 50 to 400 meters, and altitudes from 10 to 30 kilometers. Took all that data and came up with a correlation. What we wanted to capture, of course, right now, as I mentioned at the outset, we have a nominal single luminous efficiency value. I think most people would surmise that that's probably not perfectly accurate. And the first things you would look at are the velocity, the diameter, and the altitude that are going to vary. But we also wanted to be able to capture that view angle dependence that I just mentioned. So you don't have to memorize this. You can look in the paper should you want to use it. But this is the correlation which accounts for all those effects that we came up with. So lastly, we want to be able to assess the validity of this model that we've come up with. As you all know, there's a pretty scarce amount of data on large asteroid impacts for us to use for validation, fortunately or unfortunately. But we do have this one familiar case for a planetary defense relevant class impactor, that of course being Tunguska. And you guys have all seen these tree fall patterns, and I think it's fair to say that the marrow has been sucked out of the blast wave analysis or the tree fall pattern simulations. But what's been not used as much is the burn pattern or the burn area from the event. And so there's actually some pretty good data in the Russian literature on the burn. I just think this image is really cool. This is a cross section of a tree from the site. And what you want to take away here is this is a radiant burn indication. So there's charring on just one side, and then the tree has grown over that. And this is contemporary to the event. So what we're going to try to do is apply our analytic model and see if we can match this radiant burn area that was observed. And to cut to the chase, when we input this into a semi-analytic trajectory code, and we play around with some of the input parameters, we can select a 72-meter object, a 30-degree entry angle, 17.5 kilometer entry velocity, which corresponds to about 20 megatons, which for those who've studied this is probably a bit on the high side for what people think. Long story short, we're actually able to capture the observed charring area using this approach. In addition to that, we also get this slight uprange offset of the maximum burn area from where the blast epicenter was located. So obviously there's a lot that goes into this. There's a lot more detail in a recently published paper in Icarus, and I'd be happy to take any questions.
Do we have any questions for Eric? So you talk about Tunguska, which, as we know, exploded in the atmosphere, and the hot jet didn't make it all the way down to the surface. But there's some evidence from geologic record, Libyan desert glass, Stockwood glass. Pete Schultz is going to talk about another example in Chile, where that hot jet makes it all the way to the surface. Is that something you can apply this model to as well?
I guess that would probably be a separate thing. I mean, so these are all steady state calculations that are local to the object. And it seems like kind of what you would be describing would be transporting something, through the atmosphere to the ground, which is probably more in the domain of some of the other, like the blast wave simulations that Michael Aftemis has done. But yeah, it would be interesting. I mean, we haven't really started trying to apply this to some other thermal situations.
And that may be a significant component of the risk for objects 100 meters and bigger. Yeah. In fact, that in this year's scenario you saw yesterday, the Denver impact exploded. Its peak and its E-depth curve was well above the surface, yet everything came down, and that very high temperature was in contact with the surface.
Yeah, we haven't considered, but interesting.